Okay, hello guys. So we continue with our topic of Hilbert spaces. Uh, Today we are gonna do bases, and basically we're ready to move on to the next topic. The next topic is gonna be Fourier series, and all this is gonna be connected to the heat equation. And in general, the heat equation, the wave equation, the Laplace equation on bounded domains. Okay, so I'm not doing this just for fun. So let me finish our uh, last topic that we were talking about Hilbert spaces, and we said that a Hilbert space is closed. Okay, so what does it mean? So I'm gonna give you an example of a set that is not closed. So the rational numbers is not closed under we could say the we could say the under the absolute value. Okay. Meaning distance. Okay. How do we measure distance on the real line? So we have 5, we have 7, we take 7 minus 5, or 5 minus 7 in absolute value give us 2, right? So what does it mean? Why this is not closed? So I can take a sequence, and you did this in calculus 1. I can take the sequence, let's say, let x to n be the sequence 1 plus 1 over n to the n. Okay, so you take this limit, with the limit when n goes to infinity of x, and this is the limit of n goes to infinity, 1 plus 1 over n to the n. So what does it give you? So it gives you e to the 1. That's 2.71 something something something. So if you don't believe me, just make a table. So make 1, evaluate 1, evaluate 2, evaluate 3, evaluate 4, and so on. And then you are getting close to this point. If you want to see the proof of this, so you have to go to my office hours, okay? This kind of stuff I don't want to do in these videos because it's kind of extra. Okay, so it's kind of taking us out. That will be useful for you. You don't know how, if you haven't ever solved this, well, go to my office hours and we solve it together. Try to solve it first, and then I will help you to solve it. So what is this saying? This is saying that you have here 2.71 whatever e to the 1, and these points, so you get first 1, right? Then you have 1 plus 1/2 to the 2. Okay, so I don't know what is that, so let's say it's here. So all those points are start getting close to the e to the 1. But e to the 1 is not a rational number, right? E to the 1 belongs to the real numbers. But all these guys belongs to the rational numbers. So you see, the limit of this guy, of this sequence, is not in the rational, is in the real. So therefore, the rational is not close under absolute value distance. Okay. Or it's not counter the norm that in real numbers we call it absolute value. Okay, so that's one example. And now let's move on to bases. Okay, so let me give you an idea of what are we going to do all this. Okay, so we are interested in sequences because you saw, and I prepare here, Wolfram alpha is free, so I don't have to go and explain. Wolfram alpha, no, Wikipedia is free, so I don't have to justify for using it, right? So we're gonna use Taylor's theorem. You use Taylor's theorem. It's probably the most important theorem of all calculus, okay? Because that's basically the tangent line, okay, approach. So you see, that's the most elementary Taylor's theorem is the tangent line approximation. But you can do better. If you have more derivatives, you can approximate f of x around a neighborhood. Okay, so it says around a neighborhood. So around the point A, you can approximate the function f of x as this finite sum. Okay, so basically, what I want to say, recall. I think it was cute. Recall Taylor's theorem. So we want to do something similar to Taylor's theorem, but it's gonna be different. So in Taylor's theorem, you learn that if you get f of x, you can approximate f of x as the sum. So let's say you have a function, right? So you have a function f of x. So let's say this function f of x. Okay. So you can approximate this. Let's say this is a. You want to approximate this around a. So that's called a neighborhood. Or what you remember, I introduced the concept of distance. The ball on the real numbers is just an interval. Okay. So around a, you wanna make an approximation. So the best approximation to start with is the tangent line. Okay. So now that will be only using the first derivative. Using the second derivative, you'll have a better approximation. Let's use blue. So that will be a quadratic function. So it could be something like that, very close. Okay, so that will be a polynomial of degree 2. So remember, in general, here is the formula: f of x of f of a plus f prime of a x minus a, second derivative at a 2 factorial, so on. So let's write it like this. So we're gonna write it infinite sum from k equals 1 to infinity, and then you have x minus a to the k over k factorial, and then times fk a, when k is the derivative. Okay, so this is this in, so when, so I have k starts at 0 because I can have 0 derivative. Okay, so when I have 0 derivative, it's just f of a, and k to the 0, this disappears, so I have f of a. So let me plug it in here. At 0, I have f of a, because at k, when I plug in k, that's 0. So x minus a to the 0 is 0. Then plus, the next one will be f prime of a, and that will be x minus a over 1 factorial, right? The next one is second prime of a, x minus a squared over 2 factorial, and so on. Okay, so this is the Taylor's theorem, but look at this. So Wikipedia gives us a nice example here. So it's saying here, you have a function, you have exponential functions. So you start with approximations. So it says k1. So let me see if we can stop it. So this is k1, k2, k3, k4. So that means k1 is only one derivative, k2 is 2 derivatives, k3 is 3 derivatives, k4 is 4 derivatives, k5 is 5 derivatives. So basically that k is giving you the number of terms in this sum. So with one derivative, this is k1. What is happening? Okay, sorry. So k equals 1, right? Now until here, this is k equals 2. Okay, so and keep going, k equals 3, and so on. So that's how you do your Taylors. Okay, I'm not gonna do that because you guys should know this. If you don't know this, so we'll go to Wikipedia and fill these gaps. Or go to my office hours, okay? We can discuss this Taylor's theorem. So there is this approximation, right? So we're gonna do today, what we're gonna look today uh, how to prove that, okay? So you can call this f of x, so let's call this finite sum. You saw calculus 2, so this is, you can call Sn of x the finite sum of k equals 0 to n of these guys. So you're taking finite sums of this. So k equals 1, then k equals 2. So this is a sequence of functions, okay? So this is, so each of them is an approximation to the function. So this will be S1, then this will be S2, and then when you are adding more terms, it's improving. It's getting more terms. So the function is converging to the function that I want, okay? So how can we prove this? Because, you know, we are not anymore undergraduate students, and that's part of the master. How do you prove things mathematically that you understand it should be true, like an engineer, okay? So an engineer that has the same understanding than you right now. So they understand, oh yeah, it looks like the sum is converging to that one, okay? But how do we prove it? So that's what we are talking about, Hilbert spaces. That is how we prove how that is convergent. And look at this. You saw this in your calculus because you calculate the residue. Look at this, is a residue formula over here. You see? This is a residue formula. Okay. So if you take k goes to infinity, this guy is going to go to 0. So the residue is going to 0. That means the residue is the difference, okay? So, or here, you can take it here, you see? It's telling you that that difference is going to 0 when k goes to infinity. So the error is gonna go to 0. You look at that's what you are doing here, and all this is done in your calculus class, okay? And you are gonna do it. If you are talking numerical methods right now. That's really important topic, fundamental topic, okay? So that's part of we want to do this here, but we're not going to do it for Taylor because you already did that in calculus, okay? Probably not rigorously, but you understand the idea. So what we're going to do here is different. So we want to introduce Fourier series. I'm getting scared of this. Things happening. Fourier series. So in Fourier series, you don't want to approach just one function. You're gonna approach a periodic function. So the function, let's say, let me see here, and I find another, this one, okay? So you have a signal. Okay, so let me put it here, orange. Okay, so I'm gonna put it orange. So you have these lines, periodic. Okay, so that's your function. Okay, and keep going infinitely. So you wanna find an approximation for this. Okay, so how can you find an approximation for this? So this is basically practically open here and close here. Then let's go all the way close here and open here, and so on. So we want to find, so you could do Taylor theorem and you'll find an approximation around here, so it will look very good. But what about all the other signal? So Taylor's theorem has the weakness that you can only do it around 1A, but then periodicity, you are losing it, okay? So what we're gonna do with Fourier series, we're gonna do an approximation. So we're gonna find a sum, a series like that, a sum of functions such that the first one, you know, so the first one might not go really good, but probably the second one does, so the second one might look something like this. Okay, it has to be look exactly the same. Sorry, I'm not doing exactly the same. It's not perfect, right? I'm just using an approximation of second order, two derivatives. But if I do, let's say I do 10 derivatives. If I do 10 derivatives, my approximation is gonna look very good. And that's what we want to do. We want to do approximation for this kind of periodic signals. Why? Because it turns out that Fourier series is going to appear natural in the heat equation. It's going to appear natural on wave equation. Wave equation is about signals. That's what is also what I'm going to show up. So let me show you here. They have here a nice example in Wolfram Alpha. No, in Wikipedia. So you see, we go here. So they're showing k equals 1, k equals 2, k equals 3, different approximations for those lines. Okay? So that's, well, in my case, okay, these lines were, over here, they did it total. Okay, so over here, they did a little bit different, right? But, okay. But so my lines are not the same as the Wikipedia, but the idea is the same, okay? So what do we need? What else do we need to be able to understand this convergence? So we need to introduce one more definition, and the definition is it's gonna be orthogonal functions. So definition, well, I like to write it in green. So definition orthogonal functions. So two functions f1 and f2 are orthogonal on an interval AB if the inner product, so f1 f2, that in our case is integral between a and b of f1 of x and then times f2 of x dx, is 0. Okay, so for example, so let's make an example. Let's say example 1. The functions f of 1 of x equals x squared and f of 2 of x equals s cubed are orthogonal on the interval minus 1 1, since the inner product of f1 with f2 is the integral between minus 1 and 1 of x squared times s cubed dx, and this is integral between minus 1 and 1 of x to the 5 dx, and then this is the integral between minus 1 and 1 of, oh no, I can integrate right away. So it will be x to the 6 divided by 6 minus 1 and 1. So that will give me, you want a factor 1 6, then it will be 1 minus 1 So this is 0. Okay. So similarly, you can prove that the inner product between x squared and x4 is 2/7. Is different of 0. So these two functions are not orthogonal. Okay. So why I like this example? Because x1, x squared, x cubed, x to the 4, those are the ones we use here for Taylor theorem. You see, Taylor theorem, that's our basis. That's gonna be our basis. So you're gonna understand in a second why do I mean by basis. But you see, these guys are the basis. So this basis is not orthogonal. So we need, so we're gonna need something different. Okay. So we're gonna define what does it mean to be orthogonal set. Okay. So we're doing right now kind of linear algebra. But you probably didn't go all this way in your linear algebra. Definition, orthogonal set. So, so a set of functions, a set of real value functions let's call it phi0x, phi1x, and so on, or phi2x, and so on, is said to be orthogonal on an interval AB if the inner product between any of those guys, so you choose any couple, okay, phi1, phi2, phi0, phi1, any, so you choose any of those, and the inner product is gonna give you 0. Where m is different of n. Okay. So now notice something interesting. What about if you do? So remember we said that in our space of functions we will consider the norm being as the is coming from the inner product. Remember? So we should recall for us, no, for functions, we have agreed okay, we will use the following norm. At least we say different. Okay. We said that if you saw the inner product of the same function with itself, okay, what does it give me? So this is the integral of a and b, phi sub n of x times phi sub n of x, so that's x squared dx. Okay, so this guy, remember what we said, that the norm of phi sub n of x is the square root of the inner product. Okay, so the norm of phi sub n of x is really the square root of the integral between a and b, phi sub n of square x dx. Okay, most people prefer to say this. They take a square here, and then don't write the square root. Okay, so people like to do that. Okay. Okay, so notice that this is exactly L. This will be, if this is less than infinity, this belongs to L2 in the interval AB, right? So these functions will be L square or square integrable if they are less than infinity, and that's kind of we want. Okay, we want functions that they are square integrable. Why? Because the functions L square integral are a Hilbert space. So as we said before, the L2 this set is gonna be the new Rn. Okay, this is the new, because you do quantum mechanics here or you do classical mechanics. Okay, so this is the new most important space. Okay, and this was discovered or introduced the last 100 years. Okay, all these things. So at least you are doing mathematics of the last 100 years, because calculus is from the 1600. So we're improving, right? So one interesting example. You are gonna do one similar one for homework, okay? Because I need this. I need to give you some introduction to this basis, because that basis is gonna generate my Fourier series, my sine series, my cosine series. Okay, and with that I'm gonna be able to solve the heat equation problem, the wave equation. It's a very beautiful, perfect topic. But I'm gonna do more, because these topics are usually part of an undergraduate, you know. But if you haven't taken, so since the prerequisite of this class is ordinary differential equation, I cannot assume you already saw Fourier series and Laplace, wave, and heat equation. So I need to talk about this in this context. But we will do also the analytical part. So I'm kind of starting to getting you ready to review your analysis. Okay, so example 2. Let me see how much time I have. 27. Sorry, the time goes really fast. So show that the set one comma cosine of x comma cosine 2x comma cosine 3x and so on is orthogonal on the interval minus pi. Okay, so we had to do like cases. Okay, so case 1, so will be, so this is phi 0x, right? This is phi 0x, this is phi 1 of x, phi 2 of x, okay, and so on. So I need to show that any couple of these guys is gonna give me the integral is gonna give me 0. So I need to do case 1, the easy case, when phi 0 is part of it. So we have inner product of phi 0 with another one, phi sub n. Okay, so in this case will be the integral between minus pi and pi. Phi 0 is 1 times cosine, this will be cosine nx dx. Okay, so you find the antiderivative of this will be minus sine nx So what is the antiderivative of this? Divided by n, between minus pi and pi. So when I plug in my pi, goes with minus sine m pi over n plus sine of minus m pi over n. Either way, this guy is 0, this guy is 0, so I get 0. So case 2. So case 2, so the first one is special because it has 1, but the other one is any cosine. So I could have phi, let's say phi n x, phi n of x. And do that in inner product. So in that case, we have the integral between minus pi and pi of cosine mx times cosine nx dx, right? And then turns out that we have to use here an inequality to prove this. Otherwise, it's gonna get hard. So it turns out that this is the sign that cosine 1/2 of cosine of m plus n x plus cosine n minus n x dx. Okay, so you might be complaining, where did he come out with that? Well, you know, it's a classical trick for this kind of statements, right? So probably somebody did it once and then everybody just copied. But it's not that hard because you have a formula for this guy. So cosine, you have cosine of m plus m x is, what is this? This is cosine of mx times cosine of nx minus sine of mx times sine of nx, right? Plus cosine of, now you have minus over here, you see? You got cosine of mx times cosine of nx, then plus sine of, because it has minus, sine of mx times sine of nx. So with this, we have these two guys cancel, and I have 1, these two are the same, so that's 2. So I need to divide by 1/2 in order for this guy to be equal to that. Okay, so let me put it, so that's easy verification. So you will have a similar with sine, so you will have to figure out your own formula, but I already told you kind of the trick. So the integral for the first one, so we're gonna have 1/2. The integral for the first one is a minus sine m plus n x divided by m plus n. Then plus 1/2, there'll be again minus sine n minus n x divided by n minus n, and all this between minus pi and pi. And then it doesn't matter because m and n are integers, so when I plug in pi, this is gonna be sine of m plus n pi is 0, and same with minus sine of n minus n pi is 0, and the same thing for minus, so this whole thing is 0. Okay, so basically we have proved that this set is orthogonal in the interval minus pi and pi. So you can improve this set. Okay, so you can so further if you find the norm of these guys, Okay, so further, if you do the norm of phi 0 of x, you're gonna find that this is 1. The norm of, sorry, no. The norm of the first one is norm of 1, and then this is square root of 2 pi. If you do the norm of phi n of x, that will be the norm of cosine nx, that will give us a square root of pi for n equals 1, 2, and so on. So this is true. So the norm of this guy, of any of those guys, is going to be 2 pi, and this one is going to be pi. Okay, so therefore, if you consider the set, the following set, you got 1 over square root of 2 pi, then cosine of x over square root of pi, and cosine of 2x over square root of pi, and so on. So this is phi 0. Let's call it another one. Let's call it like this: phi 0, phi 1, phi 2. If you consider these guys, the inner product of any of these guys is gonna be 0, but the norm of each of these guys is gonna be 1. So this is what is called, this is a orthonormal set. Means each vector, the norm of each vector is 1, and they're orthogonal. So why do we want that? Because remember, when you are in calculus 3, in cal 3, you have a basis of E1, E2, E3, right? What is that? This is 1, 0, 0, 0, 0, 1, comma, oh sorry, 0, 1, comma, 0, 0, 0, 1, right? So turns out that if you do EI with AJ, the inner product gives you 0 because they're orthogonal. Remember, they go like this. But if you do the inner product of itself, it gives you 1. So we are trying to imitate this. Okay, why? Well, this is but it's almost done. Okay. Why do we want to do this? So suppose you are in R3. So let's talk now about bases now. Finally, bases. So suppose you are in R3. So let X is in R3, right? So you have this vector in R3. This is B. Oh, yeah, let's call it B. So then from calculus 3, I know I can find B is, let's say B is B1, B2, B3, right? So since my basis is easy here, I have 1, 0, 0 plus 0, 0, 0, so 0, 1, 0, and then 0, 0, 1. So my first element has to be B1, my second element is B2, my third element is B3. Okay, so in this case it's easy. Okay, but what about if I have a different one, right? So what about if I have something more difficult? So let me give you easy, interesting assignment. So let's say you have 21, 3, and 11. and your bases is 7, 9, 9, 10, 11, 12, and then 13, 14, 15. So the inner product is gonna be different of 0, so they are not orthogonal, right? So how can I find B1, B2, and B3? Okay, that would make it hard, right? Because these are not orthogonal. So, but there's a little trick for this. So that's a little assignment. It's not that I'm gonna collect it, but think about this. How would you make, if this is your base, how would you find B1, B2, and B3? Okay. So even further. So let's say we are in this case. We have my family of my set of cosines on my example. Let's say I get this set. So let's call this my let's call it my cosine set. Let's call this one cosine set. Or well, probably even better. So let's call it this one orthonormal cosine set. And then this guy, just like that, this guy, let's call it, this is my cosine set. This is my cosine set before orthonormalizing. Okay. So suppose I have a different basis. So let's go back to R3. So let's say we have an orthogonal basis, not normal, just orthogonal basis for a vector space. Okay. And let's say a vector space of dimension 6, let's say. Okay. Just so you are you can think that you are in R6 if you want, but and the basis is B1, B2. Oh, let me. So okay, no, sorry. Let me. No, I don't want to use the same one. Let me use U1, U2, U3, U4, U5, and U6. Okay. And then, so let X be an element of this vector space. Okay. So find B1, B2, B3, B4, B5, and B6 such that X equals, so B1 times the basis, so U1 plus B2 times U2 plus B3 times U3 plus B4 times U4 plus B5 times U5, and then plus B6 times U6. These guys are real numbers. Okay. Okay, these are real numbers. So b1, b2 are real numbers. So how can we find that? So there is very smart way to do it, and that's why uh, people understand this and saw so much potential on it. And it's the following. So this is a real number, right? This is real number. Real. I cannot not like it because b1 usually used kind of for vector. So I apologize. Let me call it alpha. Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay, so how do we do this? So we do the inner product of, we need to find alpha 1. So think how could I use inner product to find alpha 1. So stop the video and think, how could you find alpha 1 using inner product? Okay, so I assume you try. So this is what we're gonna do. So we know, let's say we want to find alpha 1. So we know that the inner product of u1 with u1, well, let's say u1 with u2 is what? Inner product of u1 and u2 is 0 because they are orthogonal. So the same thing is for u3, for u4, for so on. Okay, so let's say ui. If I is different of 1, so I'm gonna make the inner product. So let's calculate the inner product. Let's calculate the inner product of x with u1. So what is x? X is alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 plus alpha 4 u4 plus alpha 5 u5 plus alpha 6 u6, comma, because this is all x, u1. Okay, so by properties of inner product, I have the following. I can express this as the inner product of alpha 1 with u1, comma u1, plus inner product alpha 2 of u2 with u1, then plus alpha 3 of u3 with u1, plus alpha, well, let me put here, alpha 4, this is not comma, alpha 4 u4 with u1 plus alpha 5 u5 with u1 plus alpha 6 u6 with u1. Okay, so now, well, let's put it, we can do it here. So now I can take this alpha 1 by properties of inner product, right? I can take this alpha 1 out. I can take this alpha 2 out. I can take this alpha 3 out. I can take this alpha 4 out. We can take this alpha 5 out. We can take this alpha 6 out. And then we can take this alpha 3 out. So turns out this guy is 0, this guy is 0, this guy is 0, this guy is 0, this guy is 0. Okay, so u1 with u1 is the only survivor. But notice I can solve because u1 is different of 0, right? Because we said that in an inner product, the inner product is 0 only and only if the vector is 0. So I'm getting x comma u1 divided by inner product u1 equals alpha 1. So I have a formula, okay? I have got a formula for this alpha 1, okay? And this alpha 1 is gonna have a very special name. Okay, so if I make, if I, we can, well, no, let's call it just like that. This is the Fourier coefficient. Fourier coefficient of your basis. Okay, so what I'm telling you is that I should be able to give you a function, and you should be able to express that function as sum of cosines. For example, you want to prepare for next class, because I'm going to stop here. Next class I'm going to start with the more rigorosity. Oh no, let me just conclude this way. Well, oh no, let's stop it here. So what I'm saying is that I can give you a function x, and you can express this function as sum of c0, c1, c2, and so on. You can find me c0, c1, c2, and then you'll be able to express this function x, and this function x looks like this. It's going to be periodic, and then you're going to find the one in Wikipedia, that one that is here. Okay, so it's similar. The exercise is going to be similar to this. Okay, not exactly the same, but we will be able to find the approximation. Okay, so I'm going to stop it here because I think the video is already too long. So we're going to do more Hilbert. Now we're going to do focus on Fourier series. Okay, so next video is about Fourier series, different Fourier series, and then we're going to start doing some separation of variables with the Sturm-Liouville problem. Okay.